Let's see, lately we've been talking about algebraic elements, and we've looked at what it means, or the relationship between being algebraic and the degree of this extension, right? Right? So this element alpha is algebraic if and only if the extension is finite. And so we want to continue studying this notion of being algebraic and this relationship to extensions. And in particular, what we want to do now is we're going to define what it means for an extension to be algebraic. So the extension L over K is algebraic. Right. Previously we defined algebraic element, now we're going to define algebraic extension. So this extension is algebraic if every element of capital L is algebraic over K, right? So if all the elements are algebraic, then we say that the extension is algebraic. Now, let's say, that's the end of the definition. And just an observation here. So note that if we have an algebraic extension, so if L over K is algebraic, and we take some alpha in L, then, okay, so we know that well, by definition then, that means that alpha is an algebraic element, which means that the degree of the extension K adjoin alpha over K adjoin alpha over K is finite. So then, we know that this is finite. Now, it does not imply, so it's kind of a warning. So this does not imply that the degree of the extension L over K is finite. All right, so just because every element of L is algebraic over K, that does not mean that this extension is finite. And the example, right? So I mean, I guess what I'm trying to say is just because one by one we get finite extensions here, that does not tell us that the overall extension is finite. And the example here, so let Q tilde denote, or so this is a subfield, so let's denote the subfield of algebraic numbers. Numbers. Right, so those are the set of all complex numbers that are roots of some polynomial with with rational coefficients. Now, what we'll see, so later at the end of this lecture, in fact, so we will see that the degree of the extension is infinity, right? So that's sort of an example of this behavior right here. Just because the extension is algebraic does not mean that the degree is infinite, or is less than infinity. And so now, this next theorem, I don't really like the placement here. Let's actually put it up here. So this next theorem will tell us just when we can conclude that, that an extension is finite. Oh, this will be theorem 1.7. So let's let L over K be an extension. Then the degree of the extension is finite if and only if L over K is algebraic and L is equal to K adjoin alpha 1 up through alpha n for some alpha I in, or let's say alpha 1 through alpha n, alpha 1 up through alpha n in capital L. Right? So being algebraic is not enough to give you a finite extension. You need this added condition that L can be expressed as K adjoins some finite collection of elements. Right? If you have these two together, then you know that that's finite. Okay, so for the proof, right, in the forward direction, we assume that we've got a finite extension. So assume that the degree of L over K is finite. Now, we first need to show that the extension is algebraic, which means that we need to show that every element of L is algebraic over K, and then we'll show the second half afterwards. Okay, so first we're going to show that it's algebraic. So let's pick alpha in L. Then by the Tower law, what we have is, well, we have L over K adjoin alpha times K adjoin alpha over K. That's equal to, of course, L over K, which we know is finite, which forces both of these factors on the left-hand side to be finite. In particular, this piece right here is finite. So we can say, and so K adjoin alpha over K is finite. And then by a previous theorem, I think it's theorem 1.5, yep. So by theorem 1.5, we conclude that alpha is algebraic over K. All right, so what did we show? We chose an arbitrary element of L. We showed that that element is algebraic. That means that every element of L is algebraic over K, so therefore L over K is algebraic. All right, now we need to show that L can be expressed as K adjoin some collection of elements from L. And now what do we have? Well, we know that this is finite. Okay, what does that mean? Well, it means that viewed as a vector space over K, right? There's a finite basis. So, see if I can fit it right here. So now, choose a basis, alpha 1 up through alpha n, in L, for L over K. Right, and then I don't think I'm going to have room, I need to move it over. So then, let's see. Well, we know that L, that's equal to the span of alpha 1 over alpha n. If you like, you can put a little sub k there. That's who the scalars that you use in this span. But L is equal to this span. Now this span definitely lives inside k adjoin alpha 1 up through alpha n, right? This set right here, this field right here, is formed essentially by doing all possible, not linear combinations, what am I looking for? Field operations, right? You can form all elements here by doing a finite number of field operations from elements in K plus these alphas, right? Well, definitely doing linear combinations, those are field operations, so we get subset here. But then this is a subfield. This is the smallest subfield of L that contains K and all the alphas. So this lives inside L. So what does that do now? Well, it squeezes everything together. They all need to be equal. In particular, it tells us that this field is equal to this field. We can say, and so L is equal to K adjoin alpha 1 up through alpha n. So that's pretty slick. I like that. Okay, now in the reverse direction, we need to show that we have a finite extension, assuming that L over K is algebraic and can be expressed as a expressed by adjoining a finite number of alphas. So let's assume that L over K is algebraic and that L is equal to K adjoin alpha 1 up through alpha n. Now, okay, so what do I need to do? I need to show that the degree of this extension is finite, and I can do that by hitting it with the Tower law. So then, the degree of L over K is equal to the degree of K adjoin alpha 1 up through alpha n over K adjoin alpha 1 up through alpha sub n minus 1, right? So you can obtain this one by adjoining alpha n to this one. And then you walk it all the way down till we eventually get to K adjoin alpha 1 over K. Now, each alpha I is algebraic over K, which means then that it will be algebraic over a larger field, right? If you give yourself more scalars, you got more polynomials, it's even more algebraic. So we can say, so period here, so since each alpha I is algebraic over K, it is algebraic over K adjoin alpha 1. Oh, let me put a, that's fine, okay, alpha I minus 1. Right? What is that? What am I saying here? If you're a root of a polynomial with coefficients in K, then you're definitely a root of a polynomial with coefficients, or you've got more coefficients. And so what that means then is that each one of these factors on the right-hand side is finite. We can say, and so each factor on the right-hand side is finite, and so multiply that out and you get finite on the left-hand side. Therefore, L over K is finite, and that completes the proof. Okay, so now there's a couple of corollaries, and I want to prove, well, we're going to prove one of the corollaries now. So a couple corollaries to this theorem. So this would be corollary 1.8. So let's let L over K be an extension, and let A be a subset of L. Now, if every element of A is algebraic, then when you adjoin A to K, you get an algebraic extension. So it goes like this. So if each alpha in capital A is algebraic over K, then the extension K adjoin alpha over K is algebraic. So what this is saying is adjoining any collection of algebraic elements to K yields an algebraic extension. Now this actually does take a little bit of work to prove here. I'll say it like this. So first, just recall that if, let's say, Z is in K adjoin A, then the way to construct Z, or you can view Z as constructed using a finite number of field operations involving elements of K and A. So we can say then Z can, or is, constructed, or maybe can be, well, I like constructed though, constructed using a finite number of field operations involving K, or involving elements of K union A. And you know, just as a reminder, you don't have to write this down, right? That's because right, K adjoin alpha is equal to the set, remember this, all things of the form R times S inverse, where R is in V and S is in V minus 0, where V is the span, yeah, it's the span. V is the span of, what's the K span of what I call it, S sub A, I think, S sub A. And S sub A is the set of all products, A1, all possible products that you can form, A1 up through A sub, whatever, A sub T, where each AI is either in A, or it's also, it could be 1 also. So, I mean, that's just kind of the precise way of saying you can build anything in K adjoin A by doing a finite number of field operations involving elements from K and A. And that's just what this is saying right there. So, okay, so what does that mean So we can say, so there exists, say, alpha 1 through alpha n. So there exists alpha 1 up through alpha n in L, such that Z is in K adjoin alpha 1 up through alpha n, right? Do your finite field operations, and whichever ones you need to obtain this Z, right, just throw them in there, right? That is just a finite collection of them. Now, oh, whoops, did I say that wrong? Oh, yeah, sorry, I should not put an L there. I thought that was weird here. Okay, so sorry, that should be, there exists some collection of alphas in A, so that Z can be expressed using field operations involving these alphas plus the elements of K. Okay, so now, since each alpha I, or do I want I plus 1? Yeah, let's use I plus 1, is algebraic. Now, okay, what do we know? We assume that every element of alpha is algebraic over K. If it's algebraic over K, then it's algebraic over any bigger field that contains K. So each alpha I plus 1 is algebraic over K adjoin alpha 1 up through alpha I. We have that the extension K adjoin alpha 1 up through alpha I, I plus 1 there. I plus 1 over K adjoin alpha 1 up through alpha I is finite. And so now, just run the Tower law just like I did a minute ago. So by the Tower law, by the Tower law, the full extension K adjoin alpha 1 up through alpha n over K is finite. And now, by our previous theorem, so by theorem 1.7, the extension K adjoin alpha 1 through alpha n over K is algebraic. Okay, what does that mean? It means that every element in this field right here is algebraic over K. In particular, our element Z is algebraic, and that was our arbitrarily chosen element. So we can say, therefore, little z is, little z in, I guess it was really in K adjoin A, is algebraic. Okay, now, so now what? I want to return to that example. So let's say previously we claimed that the extension Q tilde over Q it has infinite degree. And now we're in a position to prove this. So we now prove this. And I'm actually going to do two different proofs. I'm going to say a few introductory words, and then we're going to split off or I'm going to do one proof, and then I'm going to just give a sort of a similar proof. So remember, what do we have here? This is this Q tilde is the set of algebraic elements. I want to show that this extension is infinite. And so we're going to do this by contradiction. So, so for our proof, suppose that our extension is finite, let's say equal to k. So then, for each algebraic number, so let's say for each z in Q tilde, the set 1 z squared up through z to the k. So what do we have here? We've got a dimension k vector space, and I've got k plus 1 elements in that set. That has to be linearly dependent. So this is linearly dependent. All right, the set's bigger than the dimension. And so thus, there exists some polynomial, just call it f, in Q bracket x with degree strictly less than k, or less than or equal to k. So with the degree of f less than or equal to k, such that f of z equals 0. So now, the first proof, I mean, these proofs are pretty similar, but I'm just going to do each one. So first completion of the proof, I just want to choose a number strictly greater than k. So let's let n be greater than k and p prime. And then what I want to look at, so let's call it w. It's going to be p raised to the 1 over n times e to the 2 pi I over n. So it's just this complex number right here. Who is this? This is well, it's not a root of unity, but it's a root of the polynomial z to the n minus p. So then, oh, I guess that's my next sentence. So then, w is a root of the polynomial, I'll just call it f, which is x to the n minus p. And you know, thinking of this as a polynomial with integer coefficients, we can apply Eisenstein here. This polynomial is irreducible. So by Eisenstein, f is irreducible over q and so what does that tell us then? Well, this is a monic polynomial, and it's a root, an irreducible monic polynomial for which this is a root. In other words, f is the minimal polynomial for w over q. You can say, and so f is equal to m sub w. I'll put a little q there. Okay, fine. So then what? So then we know the degree of the extension q adjoin w over q, and so it's going to be exactly n, right? And so we've got a basis. So then we have 1 w up through w to the n minus 1 is a basis for Q adjoining W as a Q vector space. So now since, let's see, I chose n greater than k, which means that k is less than or equal to n minus 1. So now, since k is less than or equal to n minus 1, we have the set 1w up through w to the k minus 1, up to the k, is linearly independent, right? It's a subset of this linearly independent set right there, which means it's linearly independent. But that's a contradiction. And from that we conclude, so therefore, Q tilde over Q, that's an infinite extension. So there's the first proof. The next one is kind of this, it's definitely in the same vein, but I just want to do it just because I already did it. So I want to back up, right? We said all that initial stuff, right? And so it's the same initial stuff where anytime you take a z, 1 up through z to the k, right? That set is linearly dependent. So the second proof, so let's let p greater than k plus 1 be prime. So just choose some prime number greater than k plus 1. And let w equal, so now it's going to be e to the 2 pi I over p. So now we have an actual root of unity, right? So then w is a root of the polynomial x. Wait, something wrong here? Yeah, no, x to the p minus 1, which is, this factors as x minus 1 times x to the p minus 1 plus x to the p minus 2 plus dot 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 down to x plus 1. Now, I'm going to call that polynomial f. So letting f equal x to the p minus 1 plus x to the p minus 2 plus dot 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 down to 1. We know, and now you need to think back. I know some of you did not take my Math 482 class, so you may not have done this homework problem, but we know that if you insert, so we know that f of x plus 1, this is going to be, I'm not going to write it out, this one is irreducible over q. By Eisenstein. Right, if you substitute x plus 1 for x here, you're going to get a polynomial that has a bunch of p's in it. All right, and so you can apply Eisenstein to it to show that it's irreducible. And so if you know that f of x plus 1 is irreducible, then you know that f of x is irreducible. So this is, you can say, and so F is irreducible over Q. This is a 482 homework. If you haven't seen it, it's not a big deal. Right? It's sort of a general idea that if you can substitute x plus 1, in fact, x plus any constant into a polynomial, if you get a polynomial that's irreducible, then the unsubstituted version is also irreducible. All of this over Q. Okay, fine. So then, what does that tell us? Well, we know that P is greater than K plus 1, which means that P minus 1 is strictly greater than K. So now we know that this set right here, 1 W squared up through W, what do I want? P minus, oh, let's just go to K. Up through K, so W to the K is linearly independent. Let's just make sure I did this right. So K is strictly less than P minus 1. Yeah. So this is a subset of the vectors 1 up through W to the P minus 1, which we know is linearly independent because what do we have? This is a minimal polynomial for W. So just like above, this is linearly independent. That's a contradiction. And so we can say, therefore, the degree of the extension Q tilde over Q is infinite. Okay, so that's a good place to stop for today. So we'll pick up with that tomorrow. Bye.